As the dissociation constant, let's have a look at this question over here. We have acetic acid solution that's here. It's been made with respect to sodium acetate. Okay, so we're gonna have it on the opposite side because they make each other, so they gotta be on opposite sides. Obviously, if this has a sodium within the acetate, it doesn't make sense for a sodium not to be on this side, right? Based on the law of conservation of mass. Hence why I put a sodium on the reactant side here as well, along with this acetic acid solution. Now, this is an acid. Is going to dissociate. It's going to dissociate into its respective cations and anions. Well, obviously, this is an acid. It's going to donate a proton. So obviously, it's going to be represented as our hydrogen ion as the cation. So then, where is the anion? Okay, it's obviously going to be in here because if this breaks apart, I know this is positive, but this here is a negative, and this is what we want to focus on as the anion because this here is the one that got dissociated from the acid in question. Now, we're going to be putting them all into an ice table. 0.20 initially for this one, as written in the question. 0.10 initially for this one, okay, and then here it's going to be 0 because it's not written in the question and it hasn't been produced yet. Now we're going to be doing our C, which is our change. These are all going to be 1x's because as you can see in our balanced chemical equation, this has a 1 coefficient, 1 coefficient, 1 coefficient, so they're all going to be a 1x. So we end up getting this for our EE table. Now we're going to be doing our Ka equilibrium constant expression. I'm going to be putting these values, substituting them into here. I'm going to be cross multiplying here in order to be getting my equation over here. I'm going to be putting them all onto one side across the equal sign 0 so that I can have my quadratic formula over here. Okay, quadratic formula. And then we're putting them all into here into quadratic formula. I have my positive route, my negative route. My negative route doesn't make sense, so I'm going to put an x over here. And here is going to be our positive. Okay, this here is our x value, right? As you can see, as an x value. X value is written in the ice table is our hydrogen ion concentration, which is actually what the question is asking for. So technically, this here is the answer. Now let's try this question over here. Well, Ka is equal to x times x. Why? Because technically this here is an x. This here is an x. We don't need to use an ice table. We can just kind of visualize it. So if this is x over here and this is x over here, it's going to be becoming x squared. Okay. How about our reactant on the bottom? It's just going to be this one because we obviously can't use this one. This is not going to be in the expression. It's going to be already integrated within the Ka over here, right? So we're just going to have this on the bottom. But why is it 0.10 minus x? Why can't it just be 0.10 as written here? It's because in our ice table, remember for our change, it always has to be used up in the beginning. Okay, so it has to be 0.10 minus x. Okay, so we're just going to be putting all of this into our equation over here, put it into our quadratic formula, get a positive route, negative route. Obviously this one here doesn't make sense, but this one does make sense. This here is our answer, so I'm going to be putting this one into our pH formula because we're asking for the pH as the answer. So I'm going to be putting them together, a calculator, you end up getting a 2.5 pH. Now I'll be giving you the answer shortly. These are the two main questions of the day. This is the answer to the first question. This is the answer to the second question.